Hello there, everyone. This is our second video in the grade 11 statistics and probability set of videos. So in the last video, I have presented this exercise one. You are asked to answer this, and hopefully you have that answers already. If you haven't seen the first video, so here's our exercises. You may pause the video to read them, and then let's answer this, shall we? So for number one, remember that we are tasked to um, determine the sample spaces of all of the following experiments. So number one, drawing two numbers from a fishbowl, one after the other, out of a hat that contains one numbers one, two, three, and after a number is drawn, it is not replaced. So imagine if you have a hat, and then you're going to take one number there, and then after taking one number, you will not replace the one that you got before. So meaning that is simply to say that repetition for number one for exercise one, let's call it exercise one. I'll abbreviate it into EX. Um, for number one here, repetition is not allowed. Okay, or simply we can say that there's no repetition. Repetition is not allowed, or simply to say there's no repetition there. Now, if there's no repetition, we can create a tree diagram in such a way that we're getting two numbers, right? We're getting two numbers from this fishbowl, which has one, two, three. So imagine if we're going to you make use of the tree diagram, we can do something like this. In the first draw, we can either get one, two, or three, right? So we can either get one, two, or three. So this is our first draw, and it's very clean to see that we can get that. So this is your first draw. In the second draw, since we got already, for example, if we got the number one in the first draw, there's no chance we can get the number one again because there's no repetition. Meaning, after we got the first draw, we can only get two and three afterwards. Okay? When we got two on the first draw, we can only get one or three afterwards. And if we got three on the first draw, we can only get one or two afterwards. So this is our second draw here, just to finish the illustration. Now, from here, hopefully you can see our sample space already. So what is our sample space from here? Um, Traveling from going to 1 to 2. So our sample space, again, this is how we write our sample space, like a set. So we can get 1, 2. What's next? We can get 1, 3. What else? We can get 2, 1. Then we can get 2, 3. Then we have 3, 1. And then what we'll have lastly is 3, 2. And this is our answer for number one. This is the sample space for number one. So we have 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. Notice that there's no repetition since we do not go back to the we don't put the one that we got from the hat and then put it back in when we drew it. So that's for number one. This is our answer. For number two, um, what's for number two? From the same problem in number one, but we say that there is repetition. Okay? So, okay. So we say that there is repetition. Or in short, we can also say that repetition is allowed. Sorry if I wrongly spell that. I believe there's no A. Okay, there is repetition. So when repetition is allowed, that is every time you toss you draw a number from this fishbowl, okay, after the other, you put that back in the fishbowl. That allows you to 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 draw. It's possible that you can draw the number again. So every time you draw, you replace it, you put it back in the fishbowl. So what's the tendency of this? We will have the same old for the first draw. We can get 1, 2, and 3. Okay, so highlighting that this is our first draw here. And for the second draw, since repetition is allowed, we can get a 1 again. If whenever we got 1 in the first draw, because we replace it, we put it back in the fishbowl. So we have 2, 3. Okay, so in such case, we can get 1, 2, 3 again. Likewise here in our number 2, we can get 1, 2, and 3 again. Likewise here in our 3, we can get 1, 2, and 3 again. And this is our second draw here. All right. Now, how do we illustrate the sample space? So we write here as S. So expect, of course, that our sample space has more outcomes here. Specifically, there are 3 more outcomes, the repetitions. So what is our sample space here? We have 1, 1, 1 and 1. We have 1, 2. We have 1, 3. That's it for all the ones in the first draw. How about for the 2 in the second draw? So we have 2, 1. The repetition, 2, 2 from here, 2 and 2. We have then 2 and 3. Now, how about if you got 3 in the first draw? So what we have is 3, 1. And then we have 3, 2. And then lastly, what we can have is 3 and 3. And then we close that with the curly brackets, and then that's our sample space for number 2, because we allow repetitions. The only difference of this answer to number one's answer is that there's no repetition in number 1. As you can clearly see from here, there's no repetition. We have 1 2 1 3 2 1 2 3 3 1 3 2. There's no 1 1, there's no 2 2, there's no 3 3. But here we say, because since repetition is allowed, we say that there is such, meaning that is possible. That is a possibility in this scenario. Okay, now let's proceed to number 3. Now for number 3, our um, experiment is that we're going to toss a coin repeatedly until the first head appears. So what would be our sample space for that? Until the first head appears. So imagine tossing a coin a number of times, and then you will stop when the head appears. So what would constitute your sample space? So first, what if you got ahead in the first toss? So meaning you don't need to toss again, since the condition is is satisfied that a head appears. So if you have a head in your first toss, there will be no problem. Okay. How about if you didn't get ahead of the first toss, tail, instead you got it in the second toss. So therefore you have tail and head. How about if you got it on the third toss first? Meaning you have TTH. How about if you got the first head on the fourth toss? So we have T, T, TH. And actually, we have this infinite number of sample spaces. Say you have a coin which is somehow biased to the tail in such a way that only seldom you seldom got the head. So it is possible that you have a set of outcome which is T T T T T T T, and then there's an H at the end. So we cannot actually write all those possibilities. I mean, you can get a possibility which has 100 of tails, and then one head on the 101st toss, and that's a possibility. Though it's not it seldom happens, but it's still a possibility, right? And we say that the sample space is the set of all possible outcomes. So what we want to take note here, sorry, is that the answer in this problem, okay, the answer here is infinite. Okay, so the answer is infinite. But mind you, it's infinite, but it's countable. Okay, it's infinite, but it's countable. And countability is very important here. Is one idea which is very important. Okay, so we say that it's infinite, but it's countable. Okay, how about for number four? Let's answer number four. Number four states that turn on a light bulb and measure its lifetime. So we cannot get actually discrete number of items here, because when you measure a lifetime, it starts with seconds or maybe hours. Let's have hours. So what shall be the lowest score for that? So we cannot put it on a set, we'll instead put it in an interval. It starts with 0, and we will make use of the interval notation here. So we will start with 0, because a defect light bulb may or will not, or defect light bulb will not turn on. So having a 0 will tell that it's a defect. So, and then from 0 up until infinity, it may run up until forever. Some light bulbs are can withstand that. Okay. So therefore, we have this interval notation here. So we're telling ourselves that a lifetime of a light bulb can run, okay, from 0 up until infinity. So this answer is also infinite, because we have a lot of infinite values between this interval of numbers. So from 0 to positive infinity. So we say that the answer here is infinite. Okay, it's infinite, but, or shall we say infinite and rather, and countable. Okay, rather not countable, infinite and uncountable. Sorry about that. Okay, there you go. So notice, try to differentiate number three from number four. In number three, we say that it's infinite but countable. I mean, we can still count, right? One, two, three, four, and so on. Here in number four, it's infinite but it's uncountable. We have infinite number of intervals between these two numbers, and we can have a lot of infinite numbers. Actually, you can get a lot of infinite values from 0 to 1. Only from 0 to 1. Okay, because there's a lot of numbers, there are infinite numbers in between those um numbers, when we try to think of the decimals, the fractions, and everything between 0 and 1. So we have an infinite number of outcomes, and it's uncountable. Okay, and that will be very important in the next slide that follows. So we have seen here in our example that we have infinite but countable and infinite and uncountable. In the next slide, we'll be talking about the sample space. Okay, so a remark after that activity: a sample space which has a finite or uncountably infinite, which is our third example. It's not finite though, but it's infinite but countable. So we can call it countably infinite. Number of outcomes is said to be discrete. So it's a discrete it has a discrete sample space. And on the other hand, a sample space with an uncountable infinite number of outcomes is called to be, or is said to be, continuous. So our fourth example, it has an infinite number of outcomes, and it's also uncountable, so therefore we call that a continuous sample space. So it follows that from our numbers 1 and 2, since we have a finite number of outcomes, those are also discrete sample spaces. Our number 4 is the only example which has a continuous sample space. So that's it for this video. I believe we have enough time for it. In the next video, we're going to talk about a subset of the sample space, which we will call an event. So that's it for now. Hope you'd like and subscribe and keep in touch. We will be making more of this. So thank you very much.